Hello everyone, I am Vishnu Teja Ratragada and my teammates are Vishnu Chaundur and Naresh Bolisetti. So our research talk is about the neural machine translation on Dravidian languages, and here is the link for Ankathology. And this is our introduction, this is our agenda starting from the introduction to future scope, all the steps you can see here in the slide. And coming to the introduction, so basically our research talk is about, as I said, unveiling the advancement in machine translations for Dravidian languages, confronting the scarcity of linguistic resources. So, the point of this research talk is highlighting novel methodologies and successful implementation of various neural machine translation models. So, demonstrating leading performance in translating 5 language bytes with a special focus on low resource languages. So, exploring the potential of cutting edge technologies, including transformer models and back translations to enhance the translation accuracy. And so neural machine, as I said earlier, neural machine translation is used for this project. So what is neural machine translation? This is a type of machine translation that relies on artificial neural networks to predict the likelihood of a sequence of words, typically modeling entire sentences in a single integrated model. It is an end-to-end learning approach where a deep learning model is trained to convert text from source language to the target language. So compared to rule-based and statistical machine translation, that is SMT, NMT can often produce more fluent and grammatically correct translations. This is because NMT is capable of capturing subtleties of language such as idiomatic expressions, synthetic structures in a way to previous models cannot. Despite its advantages, NMT is computationally intensive, requiring significant amounts of data and computational power of training. However, once trained, an NMT model can translate new sentences quickly and efficiently. So NMT has significantly advanced the field of machine translations and is underlying technology behind many of the online translation services available today. And this slide talks about the importance of neural machine translations for Dravidian languages. So, as you can see, the Dravidian languages includes Telugu, Tamil, Kannada, Malayalam, and these are the four mostly spoken Dravidian languages. So, these facilities the importance of anonymity for Dravidian languages facilitates seamless communication across Dravidian languages, vital for linguistic diversity in South Asia. So it acts as a tool for preservation of literary and cultural heritage of these languages. So it also ensures the digital age and information technology in the native languages. So what are the challenges in NMT for low resource languages? As I mentioned before, tokenization. Tokenization is become a challenge for NMT for low resources languages. Here we can see an example of an Urdu and an English sentences. For in an English sentences, uh, we can easily identify the delimiters and white spaces. And but in the case of Urdu sentence, it's difficult. It is difficult for a machine to identify the delimiters and divide the sentence accordingly. So tokenization is not possible for that. And challenges are some other challenges like some languages support homograph words whose meaning changes with context. For example, here in heart attack and dog attacks cat. Attack is the homograph word. Both have same word but the meaning is different. But some languages likewise some languages have multiple scripts in the like for if you take Punjabi it has two types of scripts, Gurumukhi and Shamukhi. So like that grammatical variations between languages lead to ambiguity. In the same way, code mixed language processing is another challenge. Like example, a user tweet listening to Bombay Hailate from Rajakumara. So these are some common challenges for NMT in NMT for low resources languages. So overview of Dravidian language. This slide talks about the overview of Dravidian languages, diversity and distribution. This paper provides an overview of Dravidian language family, and it's spread across South Indian neighboring countries. So you can see, as I said earlier before, Telugu, Tamil, Kannada, and Malayalam. These are the Dravidian languages. Then coming to the next slide, main elements covered in the topic. So these are the main elements covered in the topic. This involves development machine translation systems for the Dravidian languages, data preparation and pre-processing, employment of various NMT models, language fine-tuning pre-trained models, and employing back translation methods, and evaluation of models using BLEU score as the evaluation metric. So, dataset statistics. So the dataset statistics provided in the paper for the following NMT models and the Dravidian languages are as follows. As you can see, Kannada to Malayalam, 90,000 and more sentences space are used for the for this project. Kannada to Tamil, 88,000, and Telugu, 88,000. Kannada to Tulu, 9,000. Kannada to Sanskrit, 8,000. So as Tulu and Sanskrit, no monolingual data was much used due to the lack of available resources. So, and as you can see, the Dravidian language tech and uh, monolingual data is taken from the Indic Corp, that is created by AI for Bharat, and these are the data statistics for Dravidian language translations, as mentioned in this slide. And coming to the data pre-processing, three steps were involved in this data pre-processing: tokenization, machine translation, and pre-processing. As we can see in the picture to the right, so raw text, the natural language, is tokenized, and it is machine transliteration is done on that. Machine transliteration, as we talked before, it involves grapheme, phoneme, and hybrid. So these approaches are used for the machine transliterations, and it went through the pre-processing. The pre-processing step involves POS tagging, stemming, stop word removal, and etc. So this process goes through the lexical and morphological analysis and neural networks. So it involves feature extraction, ML algorithms, and post pre-processing is done like that. And after this process and after these tasks are done, it goes through the evaluation. That is B, as mentioned before, BLU is evaluation metric is used for this data went through. And tokenization. In tokenization, the raw text is tokenized into lexical units, that is the basic units. So there are three types of tokenization: sentence level tokenization, word to word tokenization, n-gram tokenization. So as you can see in the right side picture, the sentences are tokenized at sentence level, word level, and n-gram level. So next slide is about machine translation. So this it plays a vital role in application like cross language machine translation, information retrieval, etc. It's a process of converting. So basically transliteration is a process of converting a word from a source language to other target languages alphabetical system without losing its essence. So that's what machine transliteration is. It goes through the this flowchart. You can see it in the right side: phoneme based, hybrid, grapheme based. So weighted finite state transducers, they call WFST, and Extended Markov Window EMW model. So before transliteration, words are divided into syllabic units using Unicode and character encoding standards. Then each of syllabic words gets converted into a target language. So grapheme, phoneme, and hybrid. So here you can see the examples. Grapheme to phoneme. Phoneme is nothing but the pronunciation of the actual word exactly in the English language. Like we have set the examples in every language: Tamil, Telugu, Malayalam, Kannada, and English. And pre-processing techniques. So pre-processing techniques. This involves stemming, stop word removal, lemmatization, POS tagging, Unicode normalization. So we have provided the pictorial examples for each of the pre-processing techniques. So you can see we have given some languages and sentences, and stemming stem words. These are the stem words used in the sentences, and stop word removal. These are the example we have given for stop word removal. And lemmatization. Lemmatization in Tamil uh, involves reducing words to their root form based on the dictionary, as we said. And likewise, POS tagging and Unicode normalization. And here is the important topic: byte pair encoding. So byte pair encoding. So it is a simple and effective algorithm used for data compression, feature extraction in natural language processing. So it's particularly useful in tasks such as tokenization, subword regularization, and vocabulary construction for machine translation and other NLP tasks. So byte pair encoding works by iteratively merging the most frequent pair of consecutive bytes into a single unit. This process continues until a preferred vocabulary size stopping criteria is reached, resulting in a compact representation of the original data. So this byte pair encoding has gained popularity due to its ability to handle out of vocabulary words and its compatibility with various NLP models. So you can see the example here. I like playing soccer. This what is byte pair encoding does. It when it goes to the it is the tokenization here. Here you see this is the tokenization and byte pair encoding. After the byte pair encoding, here we get the correct format of the sentence. I like playing soccer. So this is what the byte pair encoding does. From here on, my friend will take on the lecture.
Hello all. Today I'm going to explain about our research talk, which is neural machine translation on Dravidian languages. So, neural-based approaches such as deep learning offer several advantages over statistical and rule-based methods. They automatically learn relevant features from raw data, reducing the need for manual feature engineering. Their ability to model complex nonlinear relationships allow them to capture intricate patterns in data effectively. Neural networks scale well with large datasets and also complex tasks thanks to advancements in hardware and software frameworks. They also generalize effectively to unseen data, can adapt to changes in data distribution or task requirements, and neural networks perform end-to-end learning, simplifying model architecture and potentially improving performance too. So they are inherently robust to noise and can learn hierarchical representations of data, enabling them to capture multiple levels of abstraction. While interpretability remains a challenge, ongoing research aims to enhance understanding of their inner workings. Overall, neural-based approaches offer a powerful toolkit for addressing the diverse real-world problems with their adaptability, scalability, and also ability to learn complex patterns being key advantages. And coming to the next slide, we have a neural-based approach. Neural-based approaches leverage artificial neurons within neural networks to process data yielding improved performance, especially on large datasets. These methods excel in learning quickly and generalizing effectively across diverse languages tasks. By employing encoder-decoder architectures, they can seamlessly translate variable length sequences from one language to another in an end-to-end fashion. This approach enhances the efficiency and accuracy of translation tasks as it can handle the inherent variability in language structures and lengths. Furthermore, the neural-based approach's ability to adapt and learn from vast amounts of data enables it to capture intricate patterns and nuances in language, leading to more robust natural translations. Overall, the neural-based approach represents a significant advancements in language processing, offering enhanced capabilities in learning, generalization, and sequence translation tasks. Sequence to sequence models like LSTM, BioLSTM, convolutional sequence to sequence, and transformers, along with the pre-trained models and fine-tuning with back translation, have revolutionized NLP. They capture long-range dependencies, bidirectional context, local dependencies, and leverage unsupervised learning for representation, significantly enhancing performance across various language tasks. Coming to the next slide, the author implemented sequence-to-sequence models and the transformer models to compare the results with the proposed methodology. Sequence-to-sequence model. The sequence-to-sequence model is a pivotal architecture in machine learning designed to handle sequences conversion across different domains. It comprises two main components, which are encoder and also a decoder. The encoder processes input sequences, encoding them into a fixed size representation, while the decoder generates an output sequence based on this representation. Sequence-to-sequence models have found extensive applications in numerous tasks such as machine translation, speech recognition, and text summarization. So, sequence-to-sequence architecture can be enhanced with the various modifications to better capture temporal dependencies and context within sequences. Long short-term memory networks, a type of recurrent neural network, are commonly employed due to their ability to retain information over long sequences. Bidirectional LSTM extends this capability by processing sequences in both forward and backward directions, capturing context from the both past and the future inputs. So, additionally, convolutional sequence-to-sequence models leverage convolutional neural networks for processing sequential data efficiently while capturing local dependencies. These diverse sequence-to-sequence variants have significantly advanced the capabilities of sequence-based tasks across different domains by enabling models to handle variable length inputs and output effectively. Their applications range from translating languages and recognizing speech to summarize text, contributing to major breakthrough in natural language processing and other sequence-related. Continuing to the next slide, we have long short-term memory, LSTM. Long short-term memory networks are a specialized type of recurrent neural network designed to address the vanishing gradient problem and enabling them to remember information over extended sequences. Suited for tasks requiring contextual understanding, such as machine translation, LSTMs excel at learning dependencies within sequences, facilitating accurate predictions. In sequence-to-sequence models, LSTMs are utilized to encode input sequences efficiently through the encoder, retaining important contextual information. And they are also used in the decoder to generate output sequences, ensuring that the model can capture and utilize context effectively for tasks like language translation. Due to their ability to handle language dependencies and mitigate the issues associated with the standard RNS, LSTMs have become a cornerstone in many sequence-based applications, playing a crucial role in advancing the field of natural language processing and related domains. Coming to the next slide, we have long short-term memory, some diagrams. The equations depict the operations within a long short-term memory cell, a type of recurrent neural network designed to address the vanishing gradient problem and effectively model sequential data. Here, the forgot gate, which is generated by F, decides which information to retain from the previous cell state, while the input gate I, it determines which new information to incorporate based on the current input and the previous hidden state. The transformation gate, which is generated by G, small g, computes the candidate values for updating the cell state. Subsequently, the output gate O, it regulates the flow of information from the cell state to produce the hidden state. Representing the LSTM's output together, these components control the flow of information through the cell, allowing it to selectively retain or discard the information over time. This enables LSTMs to capture long-term dependencies and context within sequential data, making them highly effective for tasks requiring understanding of temporal patterns, such as machine translation and also speech recognition. And coming to the next slide, by long short-term memory. By long short-term memory improves upon traditional LSTM architectures by incorporating a second layer that processes inputs in reverse order. This bidirectional processing captures both forward and the backward sequences context, allowing the model to grasp dependencies from both past and future data points, leading to more comprehensive understanding of the context. By capturing information from both directions, LSTM enhances sequence-to-sequence models, particularly in tasks such as machine translation, where here understanding complex linguistic nuances requires a deeper understanding of the context surrounding each word or phrase. The bidirectional nature of LSTM enables it to effectively capture context dependencies in both directions. Therefore, by improving the accuracy and performance of a sequence-based models in various natural language processing tasks. Coming to the next slide, we have some equations for the by-long short-term memory. By-long short-term memory enhances traditional long short-term memory networks by incorporating two LSTM layers, one processing inputs in the forward direction and other in reverse. Each layer consists of a forget gate, which is denoted by F, an input gate I, transformation gate by G, and the output gate by O. Operations. The forward LSTM processes input sequences in the standard forward direction, updating its cell and hidden state accordingly. Conversely, the backward LSTM processes input sequences in reverse, updating its cell state and hidden state based on the backward input sequence. So, by capturing both the forward and the backward context, LSTM comprehensively understands dependencies from past and future data points. This bidirectional context captures boosts the model's performance, especially in tasks requiring nuanced understanding of sequential data such as language translation, sentiment analysis, and named entity recognition. LSTM excels in grasping intricate patterns and long-range dependencies in sequential data, enabling more accurate predictions. Its effectiveness mostly lies in leveraging bidirectional information flow, allowing it to capture context from both the directions and improve the model understanding of complex consequences or sequences. Thus, LSTM serves as a powerful tool in natural language processing and other sequence-related tasks, enhancing the performance of various machine learning applications. Coming to the next slide, we have convolutional sequence to sequence, which is denoted by con2 sequence here in the slide. Convolutional sequence to sequence is an innovative approach that applies convolutional neural networks, CNNs, to sequence learning and serving as an alternative to traditional recurrent neural networks. Unlike recurrent neural networks, convolutional sequence to sequence processes input sequences in parallel, enhancing efficiency, particularly with longer sequences. And this model manages long-range dependencies adeptly through dilated convolutions, enabling it to capture contextual information effectively across various positions in the sequence. Convolutional sequence to sequence demonstrate exceptional proficiency in directly mapping the sequences between languages, making it particularly well suited for machine translation tasks. Its selection is based on its ability to capture the hierarchical structure inherent in languages, allowing it to comprehend complex linguistic patterns and relationships. So, by leveraging the parallel processing capabilities of CNNs and the effectiveness of dilated convolutions, convolutional sequence to sequence represents a significant advancements in sequence to sequence learning, offering improved performance and scalability for a range of natural language processing applications. Coming to the next slide, we have the encoder and decoder here with some equations. It provides the architecture depicts a sequence to sequence model with the encoder and a decoder. The encoder first embeds input tokens into dense vectors and applies convolutional layers to extract features, followed by max pooling to obtain a context vector. The decoder utilizes an attention mechanism to focus on relevant parts of the input sequence while generating the output sequence. It initializes with the context vector and generates each token based on the previous token, previous hidden state, and the context vector too. So the output layer produces a probability distribution about the vocabulary for each token. This model's loss is computed using cross-therapy entropy, measuring the discrepancy between predicted and actual response sequences. This architecture combines convolutional layers for efficient future extraction with attention mechanisms for capturing dependencies. So by making it suitable for tasks like mission translation and sequence generation. Coming to the next slide, slide number 28. Here, we are going to deal with the transformer model. It has some more advantages when compared to the sequence to sequence model. The transformer model surpasses traditional sequence to sequence models like RNNs with its ability to parallelize computation, capturing long range dependencies efficiently through self-attention mechanisms. It scales well with large datasets and longer sequences, overcoming the issues like vanishing gradients. The training is simpler here, and scores offer interpretability, aiding debugging. Moreover, pre-trained transformers facilitate transfer learning, achieving state-of-the-art performance across diverse NLP tasks within the minimal task-specific training. Overall, the transformers parallel processing, long-range dependency modeling, scalability, simplicity in training, and interpretability and transfer blending capabilities make it superior to traditional sequence-to-sequence models for various natural language processing tasks. Coming to the next slide, we have the transformer model here too. The transformer model revolutionized neural natural language processing in 2017 by introducing a novel architecture centered around self-attention mechanisms. Unlike prior sequential models, transformers process input data in parallel, enhancing efficiency and also scalability. These are crucial for handling complex tasks. The attention mechanism prioritizes different parts of the input data, allowing for differential weighting and comprehensive context understanding. Here in NLP, transformers excel at tasks like translation Dravidian languages, thanks to their ability to manage complex patterns and large datasets effectively. Research highlights include training transformers from scratch to tailor models for specific linguistic nuance of languages like Kannada, additionally fine-tuning pre-trained transformer models to optimize them for particular translation tasks, leveraging their broad language comprehension and further enhancing their performance in various linguistic contexts. Coming to the next slide, 30. Here we have the key features of the transformer models. Transformer models have revolutionized natural language processing with their distinctive features. They employ self-attention mechanisms to capture dependencies between words in a sequence, facilitating better comprehension of the input data. Unlike recurrent models such as RNNs, transformers process their input sequences in parallel, making them highly scalable and efficient for handling language sequences and large data sets. Their layered architectures enables the model to progressively refine its understanding of the input data, capturing intricate patterns and hierarchies of information across different abstraction levels. Here, transformers also incorporate positional encoding to preserve the sequential context during processing, ensuring accurate representation of input sequences. These features collectively empower transformer models to achieve state-of-the-art performances across various NLP tasks, including machine translation, text generation, and language understanding. So their versatility and effectiveness have propelled them to forefront of NLP research and applications, marking a significant milestone in the field. So, so from the next slides, my friend Vishnu Chaundur will continue. Thank you. Thank you for giving me this opportunity.
My name is Vishnu Chundur. From here, I'm continuing with the proposed methodology as we have gone through the sequence-to-sequence models and the transformer models. So the author has implemented a new model which is composed of pre-trained, fine-tuning, and the back translation. So pre-trained model. So the author has taken the pre-trained models from the AI for Bharat website, which is an open source, and it is in a research lab. Uh, uh, At IIT Madras, the main agenda is to develop an open source datasets, tools, models, and application for the Indian languages is the main concept of the AI Bharat for transformers. So here The main agenda is the project is working on the Indic Trans project translations for the Indian languages. So they have taken the large multi-language data sets of the South Indian languages and other parts of the Indian languages, and they have trained a model. So the benefits of this taking the low resources languages is to improve the generalization because model trained on the diverse data sets to across the various languages. It's meant to handle the low resources languages with the limited training data. Normally, they find specific task on the languages with the limited resources, it becomes easier to adapt the characteristics of the low resources languages. So data augmentation is trained on the diverse data sets due to its techniques. And for the low resources languages, the training data might be scaled, and this technique can be done by the back translation. So this will reduce the language biases. These are some of the benefits of the low resources languages by using the models. So normally, this AI for Bharat has taken this translation, this pre-trained models are done by the BERT model bidirectional encoder representation of the from transformers. These models are used. So the authors, this AI4 has taken this uh, evaluations of the BERT models. So in the pre-training the model, if you go to these websites, you can find the models. So now, whenever we are developing a model, before the pre-processing has to be done. So as usually the pre-processing is done, so the main purpose of adding the byte pair encoding is so normally in English the byte pair encoding is not necessary, but not necessary. So in case of the Dravidian languages, byte pair encoding technique is important because when when we take the vowels and the consonants, so it will provide in a compound letter, so which is not uh, normally seen in the English language, but in the South Indian language or in the Indian languages, we can see that a vowel, when composed of this consonant, we have a compound letters. So for that purpose, the byte pair encoding technique is very important. So we are seeing the pre-trained models, so how the author has taken the data sets from this AI for Bharat from the Samanthara and the Bharat parallel corpus collection is on this Indica trans and the Indica trans 2. These are some of the pre-trained models that has used in this proposed methodology. So next, fine tuning. So already we have seen that the what is the advantages of the pre-trained model is to its cost, and it will improve the performance and the accessibility, and it will regularize the uh, it will the model doesn't go the overfitting or the underfitting. So next, the fine tuning. This in the fine tuning, this process will take the pre-trained models and the additional training data sets for the on the specific task, and it is given to the fine-tuning code to get the better predictions. So the performance of the model, and it will reduce the time and the resources and better generalization and reduce the overfitting. So domain adapting the models of the specific domain on the data distribution. For example, a model pre-trained on the generalizing text data can be fine-tuned on the medical text data to make it more suitable for the task in the medical domain. The code here, the pre-trained models and the additional training data set is fed to the fine-tuning code in order to improve the. So in the fine-tuning, they have used the transformer 4x model. Uh, Normally, a transformer consists of encoder, decoder. In an encoder, the process the input sequence, and the decoder will decode the all the sequences. And this consists of the self-attenuation mechanism. So here, the self allows each word in the sequence to attend all other words and capture long-range dependencies effectively. This also consists of the positional encoding. So after running the embedding and the tokening, the positional encoding. So here, this will represent it will provide information about the position of the each token in the sequence. The main use of this positional encoding. So next, it is fed to the feed forward neural networks. It is consists of this self attenuation mechanism. So it consists of by self attenuation mechanism, which is activated. It is a fully connected layer, which is activated by some activation functions like reload. So next, is led to the layer normalization and the residual connection. So residual normalize the activation of the each layer, while residual connection allow the network to bypass certain layers, helping the vanishing of gradient problem. Next, it is mostly consists of multi-head attenuation. To enhance the representative capacity of the model, multi-head attenuation is often employed. This involves performing the self-attenuation multiple times in parallel, each with a different learned project of the inputted embedding. Finally, it is consists of encoding decoding architecture, and from the decoding, it is fed to the softmax activation function to predict the probabilities of this each sequence. Based on the probability, after decoding, we get the output. So when we compare with the transform 4x model with the baseline model, so it has more advantages. The author why he used because of this. Uh, it consists of the attenuation layers, four attenuation, quadruple attenuation layers, because for the improving the complex language patterns. So this Dravidian language has a complexity nature. So in order to understand the complexity nature, so the author has taken the transformer 4x models, this is quadruple attention layers. So when we compare, it is 4 times better than the baseline models, and the computational requirements is very less. So we'll require deals with the complex patterns, and it will take the computational time will be optimized, and the training data can be we can take the minimum or the limited training data to get the better results. So normally this transformer 4x models will use the GPU or the TPU model for the long-term trainings. So the performance is very good when compared to the normal baseline. Already we have the done with the fine tuning. So in the fine tuning models we use, for example, we have in the fine tuning, we have taken, for example, the source language is the Kannada and the targeted language is Tamil. Next, so from this fine tuning and the pre-trained models, we have converted from the Tamil. So in order to get, so whether the translated or the translated sentence in the target languages is appropriate or not, we can test by the back translation. So the main advantages of the back translation is to compare the translated sentence is exactly represent the original meaning of the source languages. So in the back translation, the source is translated to the targeted languages with additional training examples, and the target languages is converted to the source and compare the source language with the initial text or the original text. So if you see this, the original source is translated into the target languages. So in the back translation, so the target, so for example, so here the original languages is Kannada and the target translated language is Tamil. So the main agenda of the back translation, see, we have converted the original to the translated using the fine-tuning models and the pre-trained models. So the back translation is the Tamil and the targeted language is converted to the source languages by using the back translation. The step one back translation has been done using the transformers model such as BERT model. So in the translation after converting, so if we compare the original text with the translator and we'll compare. If we found any differences and reconcile, I mean feedback loop is given. So if we don't find any differences, the translated sentence is the exact representation of the original. So the output will become. So in case if there is a differences, the reconcile and the feedback is given, so they will go into review. So again, again it is fed to the transformer and one more set translation will be done. So and compare, it is like a cyclic structure. So until and unless we can get any differences, the loop will run continuously. So if we don't find any differences, the target the exact meaning of this original. So the translation has done perfectly. So this is not done with the this type of translation is not done with the transformer or the sequences and the convolution. So the author introduced because of this. The author why he introduced this methodology because so normally the translation is done like it doesn't represent somewhat like original meaning. So to mislead. So in order to get the exact meaning, so he used the back translation. Back translation, he has used the phrase sequence, which is developed by the Facebook AI research. It is an open source toolkit for the sequence to sequence learning. So you can get this phrase sequence library packages in the from the link given in the below. And why? Though he used the phrase sequence in this paper, the training model and improve the model and preparing the data and checking the work. Why the phase sequence important in this paper? So the phase sequences has make the author's work easy because he used just like a phase sequence mo- phase sequence toolkit. So to get the to explore how to improve the translation from the languages that doesn't have the lot of digital resources because low resources language doesn't we don't find in many resources. Like for example, if you take the English, it consists of like 1.6 billion data. We can get the 1.6 billion GB of the data, but when we take the low resource languages, we get like some very less. When take the ratio, which is 1,000:1, approximately 1,000:1. So when we take the one data set of the low resources, we can get the 1,000 data sets of English. So this that is why he used the phase sequence. So it will help how effective this method is teaching the computers to translate the Dravidian languages. So these are the hyperparameters that are employed in this paper. So the author has taken a sequence to sequence, he used LSTM by LSTM consequent with these following parameters, and with the transformers, he used these following parameters to compare the result. So when he used the fine tuning, that is proposed methodology, he used these other models. So when we taken the maximum tokens, so if we take the maximum tokens for the consequence or the sequence to sequence model, or it is reduced. See, the maximum tokens is 12,000 here. Here, the maximum tokens is 1,500. So it is reduced. So the complexity of the model also reduced. So the learning rate is very less. So it can easily learn through this methodology. So finally, we have translated the original text source language to the target language. That is, translation has been done from the Kannada to the Tamil. So now we want to evaluation the metrics. We have taken the example for converting the Kannada to Tamil. So now the evaluation matrix has to be done. So bilingual evaluation under study. It is one of the metrics to score to evaluate the quality of the translated text compared with the one or more references translations. So this can be done by these three steps. One is the precision. So how many words in the candidate translations appear in the reference translation. So here in this work, the author has taken the 4 gram, and generally maximum 4 gram is calculated. Beyond that, no one has taken, so maximum capacity is 4 grams. So the author used the 4 gram translation. So next, brevity penalty. So it will avoid the short translations. So brevity penalty, how to calculate this one. So next, based on the brevity penalty and the precision, the Baylor score may bilingual evaluation and the study score be calculated based on the precision and the brevity penalty. So the evaluation metrics are scaled. So now we need to compare the results with the sequence to sequence, the proposed methodology with the sequence to sequence, and the transformers. So when we go to the results, I told that the author used the 4 grams for the final evaluation. So the author has taken the main agenda is the author is to convert the Kannada to the other South Indian languages such as Malayalam. This is the original text, and this is targeted. He translated the Kannada into the Malayalam, Tamil, Telugu, Tulu, Sanskrit he used in the training. So this is the original text, and when it is translated in the Malayalam, these are the results are obtained. So the meaning of this source language is educational qualification. So when it's converted, somewhat uh, translations has been done, so which are appropriate. So from this, so when the from the results of the proposed methodology, the author's methodology is quite working for the Telugu, Kannada to Telugu. It is mostly effective when he give the ranking. So first he observed that the Kannada to Telugu. So if you see the bill score, translation is not good, one represent the perfect translation. So when we see the scores, the Kannada to Telugu it is that 0.36. And next, the Tamil is working out. Next, the Malayalam. And last, the Sanskrit and Tulu. We got low score because the Sanskrit and Tulu, we don't have much training data sets when compared to the Telugu, Tamil, and Malayalam because they have the very low training data sets. So when we train these data sets with the LSTM and BiLSTM and the sequence to sequence and the transformer models, we can see the model is going to overfit for this Tulu Sanskrit, which is not good. So that is why the back translation, proposed methodology is working. So author also compared the pre-trained models, which is developed by the AI for Bharat. So for the scoring is he has given here. And it is from the pre-trained model also, the Tulu and Sanskrit, because they have consist of data, the training data sources is very low, so the translation cannot be possible. The exact translation cannot be done. So next, finally, it plays a pivotal role in the improving of the linguistic access and preserving the rich cultural identity of the Dravidian languages, despite challenges such as limited resources and the complex syntax techniques like model fine-tuning and the back translation offer promising solutions for the Telugu, Tamil, translation from the Kannada to Telugu, Tamil, Malayalam when compared to the Sanskrit and the Tulu. So by leveraging the technology, we can bridge the communication gap among the diverse language groups, fostering understanding and the collaboration. To understand advanced NMT development for the Dravidian languages, we advocate for the expanded data sets, the development of the advanced ML models, and active collaborations with the linguistic communities. Together, we can ensure that NMTs continues to empower linguistic diversity and facilitate many connection in our in- increasing interconnected world. Scope of this project is efforts to collect the augment large on the more varied dataset for the Dravidian languages to better represent their linguistic diversity and advance in the NMT models and methodology to enhance the translation quality, particularly for the very low resources languages like Tulu, Sanskrit. So further exploration of the cross-lingual studies and the linguistic model to establish connection between the Dravidian languages and with the other families, facilitating better understanding the translation. The focus on the enhancing the digital infrastructure, supporting the Dravidian languages to ensure broad access and including the development of the languages, technologies to the specific need of their languages. So terms for the translating between. So from this research talk, we had we want to explore the translation between the English and the South Indian languages such as Tamil, Malayalam, and the Kannada to enhance the access on the online resources and preserving the linguistic diversity. So selecting the proper NMT architectures to handle the specific complexity of the South Indian languages and approaches model selection. So by them uh, utilizing this evaluation metrics like bilingual evaluation, view evaluation metrics for the translating quality is accurate and reflects the natural sounding translation, we can adopt the similar evaluation metrics to ensure the effectiveness. So finally, integrating a successful model and is a user-friendly interface for the real-world testing and the continuous improvement for the based on our user feedback. Thank you.